here, M0NTV, and welcome back to my shack and to another homebrew video. Well, I say homebrew video, this one is going to be a bit different. We're taking a kind of step to the side from our building the direct conversion receiver at the moment, because I did promise after the last video on the audio amplifier that I would do a video explaining how to design your own simple transistor amplifier. And now in my case, it was just a two transistor audio amplifier, but actually some of the calculations and things I'm going to be showing you are applicable to most frequencies. So you could kind of recalculate it and build an RF amplifier, a small signal one, so like an RF preamp or something to go in an IF stage or something like that. As Mr. Giuliano says, you know, when you know stuff, you can do stuff. So once you've got these things down, they have wider application. So now what I'm going to do today is this is going to be quite a long video because there's quite a lot of material to cover, and actually it's going to be part one of a little mini two-parter. So today we're going to cover exclusively the DC biasing, how you calculate the resistors in your amplifier circuits, and I'm going to try and explain the reasoning why you would make these calculations, and what are we actually trying to achieve there, as simply as I can. All the maths is not complex. It can't be, because I'm doing it and I'm no mathematician, right? And I will try and keep it as simple and as practical as I can. The next video we will look at the AC, the small signal analysis, and we'll look at things like how you calculate the input and the output impedance and getting more gain out of it and all that kind of stuff. If none of this floats your boat, don't worry about it, right? It's, when I first started out, there were some videos I took a look at and thought, oh no, I'm not at this stage. And that may be you, in which case that's absolutely fine. I will see you in 2 videos time when I make the next part of the direct conversion receiver. But if you are interested in having a go at this and just understanding, how do you do it, then make yourself a strong cup of something, buckle up, and may God be with you. I hope you find something of interest here, and as always, I hope you enjoy. And so here is the first stage of our amplifier. It is a very familiar schematic. It's a common emitter configuration, and we're going to operate this in class A, which basically just means the transistor is going to be switched on all of the time, which is the most inefficient of all the amplifier classes, but is the most linear and will give us the best representation of our input signal at the output, just bigger, right? But without a whole load of distortion. So that's why we're going for this configuration. Now, what we are going to do in this video is we're going to concentrate on the DC biasing. What do I mean by that? Well, all I mean by that is we are going to control the current levels that flow in this circuit, and we're also going to control the voltage levels at certain points in the circuit as well. And that's what DC biasing is for. And the reason we do it is because we want to establish what we call the quiescent operating conditions. So that just means what it looks like when you've just got DC current going through it and no AC signal. Because we need to get it working right from a DC point of view before we start worrying about adding our signal to it. And we're, I'm sure, aware of how a transistor works. So this is a 2N3904 NPN small signal transistor. And so a small current on the base will result in a much larger current flowing between the collector and the emitter. And just how large compared to the base current depends on a factor called beta, sometimes called HFE in the data sheets, and this is the gain of the particular transistor, and that can vary from one transistor to the next. And essentially what we're going to do is we're going to set all these currents and voltage levels so that when we put our audio signal waving up and down on the line there in, what we will see here, and we're going to take our output off here on the collector, will be, it'll be an inverted form because we're taking it at the collector, but that's absolutely fine. But it will be a faithful copy of what we see here, but just bigger by beta times, by the gain times. And so essentially what we're doing is we've got DC current flowing through here, and that's being amplified and flowing through here. So all we're doing really is we're hitching a ride. We're getting our signal, as it were, as thumbed a lift, our AC audio signal, on riding on the back of this DC current that's going through anyway. And because the DC current is being amplified as well, so the AC signal is. And at the output here, of course, we'll be going through a DC blocking capacitor, because we're not really interested in the DC, it's the AC we want. But for today, we are interested in the DC because we've got to worry about the DC first to get this quiescent operating conditions right and get it where we want it. So what that means is we, for now, are going to forget about the audio signal altogether. So concentrating on just the DC, that means all these capacitors will appear to our DC current as open circuits. It's like, somebody's just cut the wire. There's nothing there, which means we can simplify this and just take these out for now. And so obviously that will cut out the AC signal source as well coming in here. So let's do that now. So here is our simplified schematic, taking out all the AC bits and just leaving the DC sections. I've left the wire on the input here and the output here just so it's clear where the input and output are going to be, but we don't need to worry about those at the moment. So how do we start? Well, there's many different ways of approaching this, and I suppose it depends on what you're most interested in. If there is a particular voltage gain that you're looking to get from this amplifier, then you might start a certain way. If there's a particular input or output impedance that you're looking to get, then you might have other considerations. I am going to start with the supply voltage that we've got here. So our VCC is going to be 12 volts. So that's nice and simple. So the only other thing we need to establish at this point is what is our collector current going to be, which will be almost identical to our emitter current, at least in magnitude. Now, how do we work out what our current should be? Well, behind that simple statement is a whole world of different graphs and calculations. And I nearly showed you some work I'd done on transistor curve tracing and DC load lines and all that stuff, But the truth is that can wait for another day. I think the thing with this process is it's one of those things that, I mean, I can show you some stuff to get you going with this and to get you using it and get it working. But as you use it and you get more familiar with it, you'll probably have questions about, well, why is that value important? And what would happen if I swap that out? And so then you can kind of dig into some of the other stuff and some of the calculations that lie behind some of the things I'm going to be saying, because I'm going to make some assumptions. I'm going to use some tried and tested rules of thumb, but behind all these things are different calculations that you might want to dig into further down the line. So let's get started then. Now, I'm just going to take a tried and tested tradition, if you like, and I'm going to bias this transistor so that it has a collector current, IC, of 10 milliamps. So I'm making an arbitrary decision, and I'm going to say, right, well, I want to see 10 milliamps going from collector to emitter. So that will be our IC. Now, I mentioned before about the beta, or the HFE as it's sometimes called, of the transistor. So beta, the Greek letter. So now beta is equal to the collector current divided by the base current. So it varies. It varies from different types of transistor, but even for the same type of transistor, you know, you could fish your hand in and pull out a load of seemingly identical 2N3904s, and they would all have a different beta or gain factor, which can be problematic, but there's some stuff that we can do about that to try and minimize the effect of it as we go along. But essentially what happens, I keep talking about the current here being pretty much the same as the current here. The truth is, you will get slightly more current on the emitter than you will on the collector. And that's because if you think about the base current coming in, the base current is flowing from the base to the emitter. And then, so let's say the beta was 100, for instance. So we've got 100 times more current here than we have here. So, you know, that's easy. But here, we'll actually have beta plus 101 times more current. And you say, well, where's the extra one come from? Well, the extra one is the original base current, because remember, the current is flowing from the base to the emitter. So we might have 100 times here. We've got the same there, plus the original current flowing through. So that's why you've got slightly more current at the emitter than you have at the collector. But for all intents and purposes, really, the current on the collector is we can say is practically identical to the current on the emitter. The only difference is, of course, the current here will be in phase. Here it will be out of phase, 180 degrees out of phase. So when we come to putting a signal, an AC signal, you know, the peaks here will correspond to the troughs here. But that's not the case at the emitter. Anyway, so we're going to start actually at the emitter. Now, I'd like you to imagine for a moment that this resistor here was not here. Just imagine for a moment that the emitter was just grounded. Would that mean then that the emitter was seeing no resistance? Well, no. I mean, of course, there's always in practical terms going to be some stray resistance here and there with the components and lead lengths and all the rest of it. But there's another resistance that we have to consider, and it's an intrinsic resistance, intrinsic to the device itself, to the base emitter junction of the transistor. Now, as I'm sure you're aware, this base emitter junction functions like a forward bias diode. And actually, there is, like a diode, a voltage drop across here, which is called VBE, which is the voltage between the base and the emitter. And like most diodes, it's a voltage drop of, well, let's call it 0.7 volts. It's somewhere between 0.6 and 0.7 volts for most transistors. So this is functioning like a diode. But this base emitter junction is seeing a resistance. Now, this resistance is interesting because it's a resistance which is intrinsic to the transistor itself, and we call it little r e. And I'm going to give you a very simple equation now. Lying behind it is a much more complex one, but let me just put it down. It's 25 millivolts divided by the current on the emitter, i.e. So where's this 25 come from? Well, it's a thermal voltage, and it's because this resistance is a kind of dynamic one. So it depends on the current which is flowing through the emitter, but it also depends on the temperature that the transistor is sat in. And this is the kind of thermal voltage for room temperature. I think it relates to about 20 degrees Celsius. And depending on what the ambient temperature is, this figure goes up or down. Now, actually, this is not a very high amount, because if we do the sums here, and so we know that we're going to shoot for 10 milliamps current going through our collector, and actually we can actually say that the current at the emitter will be approximately 10 milliamps as well. So if we put this in here, that means that little r, oh hang on, get the right colour. I'm trying to put the resistances in green and the currents in blue and the voltages, when we get to them, in red, but the wheels may fall off that one, but we'll stick with it for now. So little re will be 25 millivolts divided by 10 milliamps, which equals 2.5 ohms. So it's a very small amount. But of course the problem with this is this is going to be different for every transistor. And even the same type of transistor, you know, everyone's going to have a slightly different little RE value. And of course, it's going to be different depending on what the temperature is. Well, you know, you don't really want all your biasing and the gain of your amplifier to be dependent on this current and what temperature the blooming thing sat at, right? You know, and also you want it to be able to be easily reproducible. So if I do a design here like I'm showing you, I want you to be able to go away, get these pots, put it together, and it to work in a similar fashion. The trouble is, if the only resistance we've got on the emitter is this little RE, we're at the mercy of the ambient temperature and everything else. So what can we do about this? Well, what we can do about this is we can do a very cool little trick called emitter degeneration. And what that means is that we put a resistor in series with the little RE. So this intrinsic resistance is now in series with a much larger external resistor to ground. And this has the effect of swamping out little RE. In other words, we put a much larger resistance here so that it doesn't really matter how much this fluctuates up and down, right? Because this resistance is so much bigger that actually it will be this resistance which defines the parameters of the amplifier, not this, right? So it's a clever way of doing it. What it also means as well, because when it comes to determining the voltage gain of the amplifier, and we're not really on this at the minute, but it's probably worth just doing this here. So the voltage gain, which is A, actually, when you rearrange the formulas and cancel things out and the rest of it, is essentially this resistance divided by the resistance at the emitter. So what that actually means is A ends up being RC, well, it's actually minus RC because it's inverted because we're taking it from the collector, over the resistance at the emitter. Now, if it was only little RE, obviously that's a very small amount, so that would mean we would have a very, very generous gain. But as we said, that's not so good, and actually it's more helpful for the stability of the amplifier to have more resistance here. Now it does reduce the gain a bit, so what we actually have is, hang on, let's just it actually becomes this plus little RE, but actually that's fairly inconsequential most of the time. So this reduces the gain a bit. Now you might think, oh well, that's a pity to lose all that gain. There is another little trick that we can do, which we'll get to later on, which will actually restore a lot of this gain that we've lost in the biasing here at AC signal levels, but well, more about that later. So, okay, where are we at? Well, we've talked about why we need this RE. So that's the point and purpose of this resistor, is to swamp out the intrinsic resistance of the transistor, known as little RE. But what value is it going to be? All right, well, all these calculations I'm going to be doing now are actually just simple rearrangements of Mr. Ohm's famous law. So we know what the current is that we want here. We want 10 milliamps. Well, what about what voltage we want here? Well, this is where we're going to use a rule of thumb. Now, the truth is, I think, you probably don't need very much voltage on the emitter at all for it to work. I've seen people argue that, as little as 500 millivolts would be sufficient. The rule of thumb is you would want to put a volt at this point here on the emitter. And if you could put, I'm just going to colour it in red so you can see this as a voltage point here as well as a connection. So if we can get a volt there, then actually that will keep the rest of the circuit happy. And of course, really, it's not really the voltage we're interested in. It's the resistance, but that will give us. We put a resistance there that will give us a volt, and that seems to work out okay. Now, the other interpretation of this is that you wouldn't put a volt on. You'd put 10% of the VCC, of the DC power supply. And actually, when I designed my amplifier, that's what I did, which is about a volt. It's 1.2 volts. So that's what I wanted to achieve. And so VE, the voltage on the emitter, will be 1.2 volts. Okay, if we're trying to calculate the value now of RE, this big external resistor here, what's it going to be? Well, we know we need 1.2 volts there, so that will be 1.2. And we know we want 10 milliamps going through it, so it's 1.2 volts divided by 10 milliamps, so 10 times 10 to the minus 3 equals 120 ohms. So that's why we settled on that figure in the schematic, 120 ohms for RE. Okay, brilliant. Now, what next? Well, next we're going to move round. We'll tackle RC last. We're going to move round now to these resistors here. But before we talk about this, what about this next voltage point here? What is this going to be? We're talking about this, and this is what we call VB, the voltage on the base. Well, it's pretty easy to calculate, isn't it? If we've got 1.2 volts here, and this current is flowing from the base through to the, that means this point must be 1.2 volts plus this effective diode drop on the base emitter junction. So this will be 1.2 volts plus 0.7. So we would expect to see 1.9 volts on the base. Okay, well, that's fine. 1.2 volts here, 1.9 volts on the base. So what is this business here then? Well, this is one of several different methods of biasing the base of the transistor. And there are other simpler methods, but this voltage divider method is considered to be the best. And here again, we're going to do, you remember down here, we were talking about swamping out this little RE by putting a resistor in here. Well, here, we're doing another kind of swamping out exercise. You remember I talked about this business of beta, the gain of the transistor and how it varies. The trouble is with this, of course, is that depending on the particular beta, the gain of your transistor, you can design this and you can have a certain voltage here, but you know, if the gain is different, then actually that's going to upset all your calculations. And so, you know, I could design it for mine, but if the beta of your transistor is different, then it's going to look different. So is there a way in which we can make the biasing point, the voltage here, not dependent on beta? Well, yes, there is. And that's by making this voltage divider here, and the phrase is, it's a funny phrase, we're talking about a stiff voltage divider. What it means is it's stiff because it doesn't bend. In other words, we want a lot more current going through this voltage divider, more than we've got going onto the base, a lot more. Because if you think about it, depending on what the beta is, you'll get a different amount of base current here, and the base current will go up or down depending on what the beta is. But if we've got a lot more current going through this voltage divider, actually any fluctuations in that base current due to beta will pale into insignificance. They're not gonna upset our biasing point because we've got so much more current flowing through the voltage divider that actually this bit pales into insignificance. So again, we've swamped it out, right? So we've managed to make sure that beta is not the be all and end all of this transistor amplifier. And by doing this, you can actually limit the impact of beta. Alan Woolke, W2AEW, has an excellent video on this. He sets up an actual circuit and takes 3 transistors and he plugs them in to this design. And 3 different transistors that he's picked with very different betas. He's got one kind of middle of the road one, he's got one really high beta and one really low one. And actually, you see the effect is pretty minimal. Whereas actually on some of the other biasing schemes for a common emitter amplifier, that's not the case. They're far more dependent on beta. So this is a good thing. And, you know, at the end of the day, it's just 2 resistors and a bit of calculating. So, you know, why wouldn't you do it, really? Okay, apologies, that was a bit longer than I intended. So what are we doing there? Well, we need to make sure we've got much more current flowing through the voltage divider. So the question then is, well, how much more? Well, again, the rule of thumb is 10 times more. You want 10 times as much current going through your voltage divider as you've got going into the base. So then the question is, well, how much have we got going into the base? So this is where we need to actually put some figures to this here. Now, it is possible, if you have a transistor tester, to test your transistor and find out what the beta of it is, which would be enormously helpful. If you don't or you can't be bothered, you know, you can just plug it in and hope for the best. And a data sheet will give you an idea of what the beta might be for a given current, but it's pretty wide. And for a 2N3904, I think at 10 milliamps, which is what, you know, we're running it at, it's something like the beta, something like between 100 and 300 or something like that, which is pretty wide. So Charlie Morris, ZL2 CTM, he advocates taking the geometric mean of that. And so this gives us a beta of 173. Now, the truth is, when I measured some of my transistors, I was getting a lot more than that. And if we get around to having a look at the LT Spice simulation, that gives me more than that as well. But yeah, you've got to go with something, haven't you? Very often people just say 100, you know, because it keeps the maths simple. But this is the figure I used when I was calculating my circuit. So this is the one I'm going to use here, even though actually I'm getting a lot more than that, almost double that actually, in fact. Now we know that the beta is the collector current divided by the base current. So if we want to find the base current, then it's the collector current divided by beta. And so if we do that, so that would give us so the base current would be the collector current divided by beta, which is 173. So that would be 10 milliamps over 173. So that gives us a base current of about 57.8 microamps. Wow. Okay, 57.8 microamps. So that's roughly what we're thinking the base current will be for that beta. In truth, as I said, you know, the beta will different, so it'll be different, but you know, we need to work with something. So how do we work out then how we're going to get 10 times that current through here? So what we do then is we go, right, well, if we want to work out what R2 is, so let me just change to my green resistance pen. So if we're going to say R2 will need to be the voltage, which we know, 1.9 volts, that's what we want. That's what we want to see at the base. Over, well, 10 times the base current, right? So 10 times the base current, which we said was 57.8 microamps. And so if you do the maths, that will give you about 3.3 kiloohms. And so that's why I've got a 3.3k resistor in my circuit. Fine. What about R1? Well, R1, we need to look at the voltage. Well, the voltage will be the VCC, the 12 volts, minus the 1.9 volts that we've got there. And that will be divided by 11 times the base current. So remember I said, you know, if we've got 10 times the base current going here, we've got 10 times the base current here, but we've actually got the base current as well, right? So this one sees the actual base current as well. So this is why this one we've calculated 10 times the base current. This one we're calculating 11 times the base current. So that will be 11 times 57.8 microamps. And that comes out to, well, we'll call it 16k. And which is the nearest resistor. So that's why I put a 16 kilo ohm resistor in R1. Well, we're nearly there. So that then will give us a nice stable 1.9 volts here. It'll give us 10 times the base current there, so we're not going to worry too much about if beta is a bit different. The last thing we've got to do is look at RC. Now, this is a really important one for all kinds of reasons. It's important because it will determine the voltage gain. It's important because basically it will define the output impedance of the amplifier when we get to the small signal analysis. But also it's really important because it's going to set this quiescent point on the collector. So this is the point at which this is like our zero crossing line for our AC signal. So let's think about like a sine wave kind of coming in on here. So it's going to kind of come in. So this will be our AC signal coming in. On here, we're going to see, a much larger version. And actually, it would be the opposite way around because it's inverted, but you know what I mean. But this point here is the zero crossing thing. And we need to make sure there's enough room for the positive excursion of the wave and the negative, right? And if we don't get this point right, if this zero crossing line is too high, there won't be enough headroom for our waveform and it will be clipped. And the same if it's too low, it'll clip the bottom of the waveform. And clipping, of course, will mean distortion. And in an audio amplifier, as this one is, you'll hear that distortion. But in any kind of amplifier, if it's Class A, you don't want to do that. So we want to try and set this in the middle to give us the best chance of faithfully reproducing our waveform. So how do we do it? Well, we're going to basically bias this point to about half the VCC, the DC power supply. Now I say about half because, and actually in truth when I did my amplifier, I did just do that. I said half 12 volts, 6 volts, I'll bias it for 6 volts at this. And that was close enough and it works just fine. If I'm going to do it really properly, you'd say, well, hang on a minute. I need to remember I've got 1.2 volts sat on the emitter, which, and that voltage, although it's performing an important function, that voltage is not available for the swing of this waveform at the collector. We need to consider the amount of voltage we have available to us for our AC signal to swing above and below the zero crossing line. And so let's calculate that. So let's call it V avail. So that will be the 12 volts that we've got on our supply minus the 1.2 volts that we're dropping over this resistor, which is 10.8 volts. So we've got 10.8 volts available for our waveform to swing through. What we have to consider now then is if we were to divide that 10.8 by 2, so 10.8 over 2 is 2 lots of 5.4 volts. And effectively that's what we've got then. So we've got 5.4 volts worth of space, if you like, for the positive excursion of the wave, and then 5.4 volts of negative space, if you like, for the negative excursion of the waveform. So what does it make this point here? Because it's tempting to think, oh well, we'll make this point 5.4 volts, but we need to remember that it's offset by 1.2 volts here. So actually this point will be 6.6 volts. Because what it will be is, if you think about it, so we've got 1.2 volts being dropped over there. We're going to drop 5.4 volts over here, which will mean there will be dropping, which is what we call VCE, 5.4 volts over here. So actually, this point here will see the 5.4 volts of the VCE plus the 1.2 volts to this point will actually be 6.6 volts. And actually that gives you the necessary headroom then, plus and minus, to get the most faithful representation of our waveform in. So now, again, it's a simple bit of Mr. Ohm's law once again. So if we want to calculate RC, we know now we want to see, well, we want to drop 5.4 volts. So that's got to be the calculation, actually. We want to drop 5.4 volts and we want 10 milliamps going through it. So it's 5.4 over 10 milliamps. And that, of course, gives us 540 ohms. And as I said, although I'm writing 540 in there, for mine, I didn't even go to the bother of that. And, you know, you can probably get away with just halving the power supply and biasing this for 6 volts. Because, I mean, it's pretty much that anyway. And that is the DC biasing done. And so let's just check our calculations then with a quick LT Spice simulation. So here's our circuit, just the DC elements of it here. And you can see here, if I test here, we've got 12 volts here, as you would expect. Let's check some of these other voltage levels. So if we go down to the emitter, now you remember we wanted 1.2 volts, which was 1/10 of this value here. And yeah, 1.24, that's fine. And because of the diode drop over the base emitter junction over here, we said we should have 1.9 volts on the base. So if we look at that, yeah, 1.95, that's fine. And then finally over here, remember we were looking for the 5.4 volts over here plus the 1.2 volts dropped here. So we're looking for 6.6 volts here. 6.4, that's fine. So that's pretty good. And we can check the currents. So these are a bit pixelated because this point is so huge. Yeah, so 10.3 something there. Yes, so that's fine. So we've got that flowing there. Now, the only thing which is different here is the current through this voltage divider is not 10 times the base current. It's more than that. And that's because we were calculating our base current based on a beta of 173, and that would give us a base current of, I think it was 57.8 microamps. But if we look at this model of the LT Spice models, the 2N3904, if we do the sum, so if we take the collector current there and we divide that by IB Q1, the base current, that will give us, the beta, 305. So that's a lot more nearly twice as much as we were bargaining on. So that will obviously affect things. So it means actually, instead of having, well, nearly 60 microamps on the base, well, we can see what we've got on the base. We've only got, we've got nearly half that, 33.7. So because we were bargaining on 60 microamps here, that's why we've got 623 microamps going through the voltage drive. So it's 10 times what we thought the base current was going to be. But that's okay. It just means that this is even stiffer. So that's, you know, all to the good. So yeah, that's great. That's confirmed by LT Spice. And very briefly, let's have a quick sprint through the second stage of the amplifier, which I won't need to spend much time on because I've done all the hard work in the first stage. Just to say that obviously the second stage is a different design. This is a common collector, otherwise known as an emitter follower. It's often used as a buffer amplifier because it has really a very high input impedance and a much lower output impedance, which is useful because it means it won't load down the preceding stage. It will give you no voltage amplification at all. In fact, you'll get a slight loss, but it will give you plenty of current. So it is a useful little amplifier. So all our voltage gain will come in the preceding stage, and then this will just beef up the current so that we can drive our loudspeaker. Now, it's a simpler design because there's only 3 resistors, and we'll AC couple the input when we get to it next time on the base here, and we'll AC couple the output on the emitter. Notice the collector is connected straight to the 12 volt power supply. So this resistor is the crucial one because it's this one that decides where this quiescent point is, because the signal is going to have to go up and down across this zero crossing line now down here. So what voltage do we want to see here? Well, quite simply what we did last time, half of the VCC. So if we've got 12 volts on our DC power supply, we want to see 6 volts here. And so that's easy enough to do. We're using the same terms of reference as the last amplifier, i.e. I assumed that beta was 173, even though we know for LT Spice it isn't. And I'm making an assumption based on that beta that the base current will be 57.8 microamps once again. So what that means is to calculate RE, we think, well, if we want to see 6 volts here, then half of that, and we want the usual 10 milliamps, which is what I do want, flowing through the collector and flowing through the emitter. So that's 6 volts divided by 10 milliamps gives you 600. So that's why I put in a 620 ohm resistor. And for the voltage divider, it's exactly the same kind of process, except now it's a higher voltage, because if we haven't got 1.2 volts here, we've got 6 volts here. Now in our case, actually, it's 6.3 it comes out to. So adding in the diode drop as usual, if it's 6.3 there, it's going to be about 7 here, which it is. And that's what we want to see. So in order to get 7 volts here, it's exactly the same calculation for R2. So it's 7 divided by 10 times the base current. So the base current, if we're assuming, given a beta of 173, that the base current is 57.8 microamps, that gives us 12.1 kilo ohms. So I just put in a 12K resistor. And then the top, exactly the same as we calculated the top resistor of the voltage divider in the common emitter amplifier. We say, well, what's the voltage? Well, the voltage is 12 minus what we've got here, which, as we said, is 7. So it's 12 minus 7 divided by 11 times the base current, because remember, we've got that actual base current itself going through there. 10 times there, 11 times here. So 11 times 57.8 microamps, and that comes to 7.8 kilo ohms. So I just put an 8k resistor in there, and that seems to do the job pretty well. We get the 10 milliamps going through there, and we've got the 620 microamps going through here again, because that's 10 times what we thought the base current was going to be. And so that's that. Well, to the 2 people still watching, well done. But seriously, thank you very much. If you have watched this video, apologies that it is a bit of a long one, even for me. And just to reiterate, as I always have to, I'm not an expert. I'm just a keen amateur, right? And that the stuff I've presented, I'm not saying is the best way, or certainly not the only way of doing any of this stuff. It's just the way I do it, and I offer it to you in the hope that you might find something helpful here as well. Until the next time, look after yourself, take care, see you on the next video. Bye bye.